I once encountered a real-world case involving a factory capacity expansion. The team replaced an old 1000 kVA transformer with a 2000 kVA unit. Both units had a short-circuit impedance, or UK%, of 4%. While they upgraded the main breaker from 2000 amps to 4000 amps for the higher load, they overlooked one critical parameter: the short-circuit braking capacity, ICU. They kept the original 50 kA rated switchgear. Shortly after commissioning, a short circuit occurred in the low-voltage cable. The instantaneous short-circuit current, ISC, surged far beyond the breaker's 50 kA limit. The resulting arc flash destroyed the entire switchgear in seconds. What caused this disaster? What is the engineering logic behind the short-circuit impedance? Let's break it down. The short-circuit impedance, UK, is the primary shield that limits fault levels. According to IEC 600765, here is the symmetrical short-circuit current formula. The maximum short-circuit current usually occurs when Zs approaches 0. The formula can be simplified to ISC equals IN divided by UK, where IN is the rated current. This formula reveals a critical inverse relationship. The higher the UK, the lower the fault current. Circuit breaker manufacturers design and manufacture circuit breakers with different current braking capacities. Higher braking capacity breakers are significantly more expensive. By selecting a transformer with a larger UK, you can specify lower rated downstream breakers, significantly reducing hardware costs. Let's move into the accident simulation. Red line means breaker's braking capacity. Blue line means short-circuit current curve, scales with transformer capacity. Dot means maximum prospective short-circuit current, determined by UK. If the dot remains below the red line, the system is safe. In our case, the 1000 kVA unit produced 36 kA, well within the 50 kA breaker limit. However, after upgrading to 2000 kVA, the fault level jumped to 72 kA. This far exceeded the 50 kA limit, placing the system in a danger zone, where a close-in short circuit may lead to an electrical accident. However, we cannot simply increase UK indefinitely. High impedance comes at a price. 1. The higher the manufacturing cost of the transformer. 2. The high voltage drop. As the current passes through the transformer's internal impedance, voltage is lost, calculated as above. Beta means load factor. RK%, XK% means resistive and reactive components of the impedance. Phi means phase angle of the power factor. The formula shows that a higher UK leads to a larger voltage drop under the same load. Let's back to TechBridge Lab. Let's assume the load is inductive, with a typical power factor of 0.85. Phi approximately 31.8 degrees. About 10% of the total impedance UK is resistive, UR, while the rest is reactive. When the other conditions remain the same, increasing the short-circuit impedance results in a larger voltage drop, and the U-beta curve becomes steeper. In practical terms, this leads to poor voltage stability. When the load increases, the voltage drop also increases. As a result, voltage instability becomes more noticeable under heavy load conditions. Beyond individual performance, UK dictates how transformers work as a team, according to IEC 60076-8. For successful parallel operation, the transformers require the same relative short-circuit impedance. Applying Kirchhoff's current law, mismatched impedance leads to severe load imbalance. If two 1000 kVA transformers both have 4% impedance, they share the load 50-50. If we change transformer 2 to 6%, transformer 1 will take 60% of the load, while transformer 2 only takes 40%. The unbalanced load is up to 20%. But the IEC standard also recommends that this type of unbalance be limited to 10%. The unit with lower impedance TR1 will overload prematurely, potentially triggering protection trips. Meanwhile, the unit with higher impedance TR2 remains underutilized, limiting the total output capability of the bank. That's all for today's video. In our next session, we'll dive deep into how to make the right selection in engineering design. If you like my video, don't forget to hit that like and subscribe button. This is TechBridge. Stay curious, stay professional. See you next time.